Welcome to Study Loop.
Is in the 4s state, n is equal to 4, we're told that the energy of the sodium, E sub n, is equal to negative 1.947 electron volts. So what is the effective net charge on the nucleus seen by the electrons, and on average, how many electrons are screened by the nucleus? So to find the effective energy, that's Z sub E, Z effective, or the effective charge, Z sub E, we're going to use this equation. The negative sign here comes from the fact that we're dealing with electrons. Then you have negative 13.6 eV from the ground state of hydrogen here. So we can rearrange this to solve for and we find that Z effective, which we're calling B, is equal to the square root of n squared, which n is equal to 4 here, 13.6 electron volts, because the negative signs cancel. Oops. Divide by, that's 18.6 the energy value. 10 divided by 13.6 eV. And the electron volt values cancel because E sub n is also an eV, so we don't need to write electron volt. Z effective is units. So carrying out this operation, we find that Z effective here is equal to 1.51. Oxygen is one of our answers for part A. Then it also wants to know the amount of electrons that are screened by the nucleus. So we're dealing with sodium, which normally has a charge of 11 electrons. So we have 11 minus 0.51 from ZF. So 11 electrons minus 1.1 equals 9.449 electrons. Maybe to indicate that we're talking about electrons, we can E minus. Okay, and now for B. So we know that the charge of the nucleus is 19, but it also occurs that 17.2 is screened by the electrons, right? Because we have, therefore, the outer electrons observed are going to be 19 minus 17.2, or 1.8. So we can say that Z effective, this is part I of B, by the way, Z effective equal to 19 electrons, so we can call this 19 minus 17.2 electrons. So this gives us 1.8. For part 2, the electron energy due to shielding is what we're asked to find. Part 2, we have E sub n, and then we're just using the same equation that we used in part A. So this is negative Z effective by n squared, where we found effective to be 1.8, and n is still equal to 4 in this case, and this by 13.6 electron volts. So plugging in those values, we find that this is negative 2.5 electron volts. We can box that in as our solution for part 2 of B.